Hi, today I'm going to show you a live demo on RacEr GPU on PyTorch, some of the PyTorch applications. So in this demo, I'm going to show you about Lanet 5 architecture. So this is based on a gradient-based learning algorithm applied to the pattern recognition to the for the documents. So specifically, I'm going to show demo on page number 7 here. Let me jump to page number 7. Okay, uh, so I'm going to discuss about the architecture of this LANet 5. So I'm going to move to the next slide and show you about explain about this architecture and then after that I'm going to show you demo. So in the figure, you can see that. Before going to the figure, I would like to give some little bit fundamentals about the in a pattern recognition. So how do we recognize the pattern and how do we train it and then how we measure the error and so forth. So in this case, so YP is the recognized class label of pattern ZP. So ZP is the pth input pattern, and the W represents the collection of adjustable parameters in the system, and EP is loss functions, measures the discrepancy between DP, the correct or the desired output, and the output procedure by the system. And the EP train, which is in terms of weights, is an average of errors, EP, or set of training parameters. You could see that Z1, D1, and Z2, still ZTP, TP. So the key influence is to minimize the E train. And if you look at the figure, above figure, so the layer C1 is a convolutional layer with 6 feature maps. Each unit in each map is connected to 5 by 5 neighborhood in the input. The size of the feature maps is 28 by 28, which prevents the connection from the input from the falling of the boundary. C1 contains 156 trainable parameters and 122,304 connections. And layer S2 is I would say subsampling layer with a 6 feature map, size of 14 by 14. Each unit in each feature map is connected to 2 by 2 neighborhood in the corresponding feature map in C1. The 4 inputs to a unit in S2 are added, then multiplied by a trainable coefficient and added to the bias. The result is passed through the sigmoid function. So layer S2 has 12 trainable parameters and around 5,880 connections. Layer C3 is a convolutional layer with 16 feature maps. Each unit in each feature map is connected to several 5 by 5 neighborhoods at an identical locations in a subset of S2's feature map. Layer S3 has 1,416 trainable parameters and 151,600 connections. And the layer S4 in subsampling layer with the 16 feature map of size 5 by 5. Each unit in each feature map is connected to 2 by 2 neighborhood in the corresponding feature map in C3 in a similar way as C1 and S2. Layer S4 has 32 trainable parameters and 2,000 connections. So if you look at layer C5, C5 is a convolutional layer with 120 feature maps. Each unit is connected to a 5 by 5 neighborhood on all 16 of S4's feature maps. Layer C5 has 48,100 trainable connections, and finally layer F6 contains 84 units and is fully connected to C5, and it has 10,164 trainable parameters. So connection label, as you've seen, the connection labels are labeled with the CX, subsampling layer labeled with the SX, and and the fully connected layers are labeled FX, and where X is the layer index. So in this example, we use a subset of 10,000 training image, but we use the full 60,000 training samples. The resulting database was called from MNIST dataset, and size normalized to 20 by 20, and centralized of center of mass in 20 by 28 fields. So on all cases, 20 iterations for performing each passes, and the value of the global training rate was considered the zeta, which is decreased on average on each pass 0.0001. So before showing this example, I'm going to tell you about how this is going to work in our RacEr GPU. So before running this, so if you don't have an AWS account, I suggest you to have an AWS account. On the right side, you can see the flow graph here. So just go to this link and register yourself. And then in that, once you have an account, once you logged in, then there is an AWS marketplace. So in the AWS marketplace, just select FPGA developer AMI, then you can get uh, F1 instance settings, the configuration for F1 instance, and then once you configured for instance memory, how much your storage you required, and what is the IP preference and so forth. Once you have that, and then once you launch the instance, you connect instance to either SSH or PuTTY. And then once you have that, and assuming that you loaded our FPGA image and sample applications in your account, so the method to run any application in a RacEr is that, so RacEr has 412 cores in 2D mesh network, and it has an API. In case of PyTorch, it is a RacEr PyTorch API, as you can see on the box here. So in case of Python, it's a RacEr Python API. It accepts the only Python scripts or PyTorch scripts. And then on the back end, this scripts running in C or C++ compiler. So whatever the applications of C, C++ Fortran are running on the back end is in a Vivid compiler, which is a native POSIT compiler. The similar application you can run in x86 CPU with the GNU C or C++. With that, I'm going to take you to the session. I usually connect through a PuTTY, so now I'll take you there. So first I'm going to show a demo on RacEr. Then after that, I'm going to show demo on x86 machine. So now we are connected to F1 instance through PuTTY. So in order to run PyTorch scripts, we just need to type make equation. So it's gonna do the regression test for linear 5. So it takes about a minute or so. So it depends on the network latency. Okay, so yeah, now this passed the regression test, and it's about 98% accuracy. So this is using our RacEr GPU. So the main program you can see at test lanet Python. Oh yeah, this is a Python script. So this is about the network, how we design the network. So and training routine, uh, and the test routines as well, the model. Uh, so the data we have taken from MNST and so forth. Uh, so yeah, so this is the Python script. Now we'll do the same thing for x86 machine. So in order to run that script in x86 machine, you just need to say so the Python. I think let's have this. Okay, Python telnet 5. Okay, now it will run the same test script for in Intel machine. Yeah. So the accuracy here also 98%. In most cases, usually what happens is that usually in x86 machines, it's a floating point. The accuracy is 1 or 2% less compared to uh, uh, the POSIT based. Most of the time it depends on the test based data sets. So sometimes its accuracy is almost equal to our POSIT based. Sometimes it's less. It depends on how it generates the random numbers. Okay. All right. So yeah. So that's it. So if you have any questions, please do get back to me or send us an email. Thank you.